Hey, what's up, guys? This is Chung here. And so today, this time, let's talk about this another graph question problem, all right? Called uh, this one is number 323. Number of connected components in an undirected graph, right? So you're given like a number of the of the nodes, right? From 0 to 4, total 5, and a list of edges, right? So 0 to 1, 1 to 2, 3 to 4, right? So now you need to get how many components, right? Basically how many subtrees or how many subgraphs does this one does the those two the will those edges form, right? I mean, this is like similar like the number of islands, right? But in this case, it's a it's a graph, right? So I think today I'm gonna talk about two solutions. The first one I'm gonna use the DFS, the depth first search, and the second one is gonna be the UnionFind. Okay, so I think depth first search DFS is pretty straightforward, right? Basically, we just start for, we try, right? We try each n here, right? For each number in n here, we follow the path, right? Until we have visited all the nodes inside this graph until there's no more like edges, right? That we haven't we, in, unless there's no more nodes that we can reach, which we haven't visited before. Then we stop, right? And then we just keep going until we have looped through all the number five here, all the five numbers here. So how do we do it, right? So for the DFS, first we're gonna define a DFS method here, right? So it's gonna be a node here, right? hmm And since we're gonna record all the visited nodes here, we're gonna have a global visited set here, right? And like I said, and uh, yeah, also let's define an answer first, right? The gonna be an answer here. It's gonna be the sub like the components, right? How many components? So we set it to 0 here, and then we just do a for loop, right? For I in range n, right? So first we check if I is not in visited, right? If it's not in visited, then we do a DFS here, and right. If it's already visited, we just skip that, right? If it's not the visited, then we know we find another like component here, right? And we do a DFS I, right? Basically, we just starting from this node, and we'll loop through all, all the nodes, right? And in the end, we just return answer, right? But before doing this, right? So let's initialize this graph first. We need to have a graph, right? So that we can start traversing the graph here. So same thing, I'm gonna have a default dictionary here, list, right? Mm. And for edges, right? For edges and for edge, sorry, in edges, for each edges, we're gonna have like basically node one, right? Node one and equals to edge 0, right? Node 2 equals to edge 1, right? So since this is like an undirected graph, I'm gonna we're gonna have like we're gonna have two edges here. First one is from node 1 to node 2. Node 2. Second one will be from node 2 to node 1, right? Right, that's how we build the graph here. So, and then in this DFS, right? Yeah, so here, every time we loop through, when we get a new node, we just don't forget to always add this new node to our visited set first, right? And then here, for neighbors, right? We can call it neighbors, I think, neighbors. For neighbor in graph, right? In graph dot node, if right, if neighbor has not been visited, not in visited, right? We do what? We visited first, right? Visited. We added to the visited set here, right? And then we'll do another DFS, right? So basically, that's how we do DFS, right? Basically, for example, here, let's say we start from 0, right? We start from 0 here, and then from 0 we find 1. From 1 we find 2. So by the time we finish uh, processing 0 here, right? By the time we're processing 0, we already have this visited sets have 1, 0, 1, and 2, right? So and then the next time I equals to 1, we check. Okay, so we already have visited I before. We skip 2, skip, and then 3. Okay, we do another DFS here and, until we have loop through all the numbers, right? I think that should do it. Yeah, cool. So um, then what's the time complexity here, right? So the time complexity here, as you can see here, so first for loop is this one, is the edges, is the edges of the number of edges, right? Basically, how many edges in this like in this graph? Let's make it m, right? M edges. And another one is another for loop is gonna be this one, so n, right? So notice that although you can it seems like for each of the n here, so we'll do another like DFS. In the DFS, we'll be having this another nested for loop here, right? So you'll be thinking about, okay, maybe this is n times something times the neighbors itself. But notice here, since we have this visited set here, right? That will make sure we'll be only visiting this node once, right? So there won't be any nested uh, process for each node here. We'll only visit this node once. So then it's gonna be m plus n, right? N is n, m is the number of edges, and since we're using the visited here, so uh this check and this check, they're they're both O1, right? So that can make this like as the second part ON and the first part is OM. So in total it's O M plus N, M plus N. How about the space complexity? Um, I think it's pretty obvious. We have this like the graph, right? So the graph will be and also this visited, right? So the visited is going to be n, right? We're going to store n node here, and the graph will also be n elements, right? So then the space complexity is going to be O to 2n, which is going to be the ON, right? Uh, okay, I think that's for the DFS, right? Okay, now let's do a union find. So So first, what is a union find, right? So a union find and a union find is this one. So every I mean at the beginning, right? At the beginning there's like numbers, right? From 0, 1, 2, 3, 3, and 4 and 5, right? So in a union find, there are like two key method. The first one is find, right? And the second one is union, right? So basically the union find, the idea here is that we're giving this number from 0 to 4, right? There's five numbers, and we're giving these edges. With all the edges, we can form these components bottom up, right? How, right? Because each of the components, they will have one and only one like root node. Like for example, right? You can also call it like cluster ID. So in this case, 0 is the root for this component, and the 3 is the root of this component, right? And while we're traversing this edges, and we're forming this like the parent and the child and the parent relationship, and in the end we can just see, okay, how many roots, right? How many roots will can this like edges form, right, in total? And then we can see, oh, there are like two here, so then the number will be two in this case. So by the time we finish traversing all the edges here, or all the two nodes here, in the end we'll be only having one root node here. Then that's why we only have one number here, right? So how do we do a find here, right? And then, sorry, so then how are we constructing this like uh, union find data structure? Mm, so first we need to create the roots, right? So the template is this. First, we need to create a roots array here. So the roots array will be the same as those numbers, because at the beginning, each node has its own component, right? Basically, let's see here, right? So the roots represent, okay, for index 0, right? Or for the number 1, what is the root of 0, right? So at this moment, the root of 0 is 0, right? And the root of 1 is 1, the root of 2 is 2, so on and so forth. And when we do the find, right? So the find is this, like let's say there's like 0, 0 and 1, 1 and 2, right? Here. Let's for example, we have this components, right? So in this case, 0 is all pointing to itself. It's 0, right? Assuming 0 it's the root, right? And then 1, right? So the 1 is also pointing to the root, and the 2 is also pointing to the root. So what does the find do? So the find is just keep going up, right, until it finds the root node, or until there's no more parent node. So for example, if we do a find 1, it will give you 0. When you find 2, it will also keep going until you get 0. So basically, the find can tell you what is the root node of this x, right? And then what does this union do, right? Okay. So union will basically union two subcomponents, x and y, right? Assuming let's we have a 0, 1, uh, and 2, right? And then we have 3, 4, and 5, right? Let's say we have these two components, right? So and at this side the root is 0, and at this side the root is 3. And if we have a, let's say, if we have uh, a union, right? So let's say the union. So the union, we will be union the any node. We don't have to be union this root node. Let's say we're union like uh 1 and 4, right? Let's say we're trying to union 1 and 4. And then when we do the union, we'll basically for each of the element here, we'll call the find method first. Basically for each of the union the element we wants to union, we always find its root node first. And if we find the root node first, right, and then we'll be basically we'll be assigned either this one under this will be assigned this root node under 3, or under assign 3 under 0. That will be the second like concept. So we're gonna have like a ranking system here, right? Because we can do either we can do either one, but we don't want to keep assigning and over, because that will and so in this case I think the rank, right? So we'll be having another like a rank array here. At the beginning there will be all 0. So the rank is the rank of the current root, right? So in this case the 0, that's the 0, and 3 is 0, 1, 2, 3. That's the rank of this root. And when we do the union, since we have two options, right? Since we can either uh, uh merge a merge this one to under this one, or the other way around. How do we decide, right? So we do a rank. In this case, I think it's you can think of like the rank doesn't have to be same, but in this case, so the rank will be at the height of the tree, right? So in this case, the height is I think this is 2, right? And this is 3. So which means we'll be merging this 3 under 0, right? So when we do the merge, we always merge the root node. Why? Because you know in the if we merge 3 to 0, and when we do a find, right? We try to find 4. We only need to traverse like uh back uh once, or like basically it will have like lower overhead when we do the traverse find. That's why we maybe this is not a good example. Let's say there's like some other nodes here. Let's say there's like 6, 7, or something, right? And because if you do the other way around, if you assign 0 under 3, you will have all this 2, 6, 7, 1. When you do the find, there will be like more overhead. So that's why we always assign the lower rank one to the parents to the higher ranker one's parent. Hmm. Okay, so I think I have discussed about pretty much everything. I'll try to code, and while I'm coding, I'm hoping I can give you guys some more details about the union find, right? So like I said, first it's gonna be the find, right? No, let's do let's do roots here. Let's do array roots here. So like I said, so at the beginning, each root is the same as a number, right? That's the first step. So we're gonna do a range n here, right? Basically do a range n, and we convert it to a list, and then the roots will have the 0, 1, 2, 3, 4, right? And then the second one will be ranks, right? Ranks, and ranks will be okay at the beginning, right? At the beginning, sorry, it's all zero, and we just and the length will be in here. So and then we have to write the first helper function, which is the find, right? So let's say we find x, right? We find x, and what do we do? We find x. If we don't find x, uh, like like we discussed here, let's say there's a like 0, 1, sorry, 0, 2, 5, 4, 3, 4, 5, right? So let's say if we try to find 4, we just keep going back, right? But there is like a improvement we can make here, right? It's called path compression. So what do we do here, right? So as you can see here, so during the find, right? Since we're going to keep going back, right, all the way to the top, we can flatten. We basically we can flatten this tree, right, to be basically, let's say we try to find 4, right? And we find there's 3 and there's 2. So what it's gonna be? So basically, we're gonna move 2. First, we'll be moving 4 to pointing to 0, and then we also be moving 3 pointing to 0, right? So that's gonna be a 0. So by the time we finish doing the find for 4, we'll have this like 2, 3, and 4 and 5, right? Because we're going up anyway, so we will just do some improvements while we're doing the find, right? So because after flattening the tree here, next time, right? Next time when we find 4 and 3, there will be O1, right? So there's only be O1. Otherwise, if we don't do this one, don't do this like path compression, it will always be ON, right? For this find method. That's called the path compression. And okay, so let's finish the implementation. Finish implementing this one. So mm, okay, if roots, right? If roots. Okay, okay. So first, I think this is a number, right? And the roots, the index of this number is the roots, right? Because the 0 is also, let's say for example 0, 0, the index 0 will be the basically this roots, right? The roots x, right? Sorry, the roots x. This is the index, and but it's also serving like a number here, right? So the index zero's roots, if it does not equal to the x, right? We do what? We just keep doing it, right? We keep traversing up, right? But meanwhile, we also want to like assign, right? We want to update, right? We want to update this like this current route to the par to the I'm sorry, we want to update current node uh, a root node to be the parent the cluster, the very top one, right? So we're gonna use like a find method, right? So find roots x, right? Basically, so when we do a find here, we will keep going back, and then meanwhile, once it's finished, we just return assign the the result from this recursive call to the current roots, right? So in the end, once this one reaches to the end, uh, everything returned from the find will be the very top node, right? And in the end, so that's what we do it. We return the roots, right? So by the time we do the first return, this roots dot x will be the very top one. That's how we do the path compression, right? And then there's another one called union, right? Union, union. So with union, we will be doing like x and y, right? So yeah, and oh, and by the way, so here we can either return roots x or x because at the very last find recursion cost, this will be true, right? So then here it doesn't really matter if we return either one. Either one is fine. So like I said, so we're gonna have like a parent root one, right? Let's call it the root one here. We need to find the current, this one's the root for this one, and then root two, right? And okay, so let's see. Okay, so we have the root, right? And then we need to get like what we said, we need to compare the rank of these two nodes, of the rank of these two roots, right? And well, actually, so yeah, okay, let's do it. So then we'll have a rank one and then rank two, right? The rank one will be the ranks, right? The roots one's rank, and rank two be the ranks dot r2, right? So if rank one is smaller or it's greater than rank two, right? So it means we want to assign the rank two's parent. Sorry, we want to assign the root two's parent to root one, right? That's how we merge the so how we or union, right? So basic parents R2, right? And equals to R1, right? And else if else if rank one is smaller than rank two, right? So then else if in this case, same thing. Since R1 has a smaller rank, then we'll be assigned R1's parent to the R2, right? And then else, right? Else here is like if they're the same, right? So what do we if they're the same, we can pick anyone, right? Since that it doesn't really matter if we assign R1 to R2 or R2 to R1. Let's say we pick the first one. Let's say we assign the R2 to R1, right? And then in the end, we need to increase, right? Increase the ranks R1 by one, right? Because that's how we I mean maintaining this rank basically. Yeah, there could be other ways, but in this case, we every time we assign when they're equal, the same, we just increase the other side by one. And yeah, so that's how we implement this find and union, right? So that's a union, that's a find. Basically, every time when we have a union, we'll be basically updating this this roots array, right? Yeah, okay, right, roots. Okay, so we have those two things now. We all we need to do is to what? To loop through the edges, right? Edge from edges, right? For each edges, what do? We do union, right? We do union. We try to construct this this parent and child relations, right? We do a union. We do uh edge one, right? Edge one, zero, edge one. Right, right. So once we after we have processed all the edges here, we'll have a roots here, right? So what do we do, right? For each of the roots, basically, and basically at this moment, So each node, each number will have its roots here, right? I'm sorry, the parents. It's not roots, it's the parents, I think. I should call it parents here. And then all we need to do is we just return how many distinct common roots does all the numbers have, right? Just do this, right? Do a length, do a, since we're doing a distinct, I'm going to do a set here, right? Uh, set uh, basically for each of the numbers, we'll be calling the find, right? Uh, find find x x for x in range n, right? Yeah, so for each number here, since we already have this roots array here, we'll be using the find method to give us a common one. And then in the end, since this is going to be array here, right? And we'll have a set, right? And then we do like a length of the set. So basically, set will give us the unique distinct roots, right? That's the basically that's give us the final number. Uh, else if oh yeah, sorry, this one. So many stupid mess arrows here. Cool. See, it passes. Cool. That's how we do it. I think I was thinking while I was coding, I think here we can check, I think R1, I think we can check if it's they're not same, then we should do the following. Otherwise, we don't need to continue, right? So if R1 is not equals to R2, right? I think if they have the same common number, common roots, we don't need to do all this thing here. We can just do a if check here first. I think it should still work. Yeah. Oh, cool. It's much faster. See, since we if it's if they're the same, they have the same, they are under the same tree. We can just simply ignore the rest because there's no need to union them because they're already unioned, right? And cool. I think that's the union find algorithm. So basically, two uh two key functions here. First one is the find, and you're given like a number here. You just keep looking for the if the current one basically, right? So if the root does not equals to x, if the parent is not itself, right? Basically, if the parent of this node does not equals to itself, then we just keep going up until it's the same, right? Because remember, the 0, 1, and 2, 2, 3, right? So the 0, right? The roots of 0 is 0, right? It's itself, but all the others, 2 is 1, right? 3 is 2, right? So that's why we can keep going up, right? And also remember, notice that there's a path compression concept here. So while doing this like loopings, we are also updating the current node's parent, right? And then in the end, we just return that. I think here, like I said, I think we can just return the x here. I think it should have the same. No, okay. Ah, yeah, sorry, I think too young, too naive. Yeah, I thought this one should also work, but just forget what I said about, oh, since this one is the same, we can also return x. I think there's something I didn't get here. So, and oh, I see why. Because this is like a recursion call. So if this is not the same, we'll go here first, right? And then by the time this recursion is finished, the roots.x already got updated, right? And yeah, it's already got updated. So we can only return this updated one. We cannot use the original x here. Yeah. So okay, so and then that's fine. And the other one is a union, right? You're given like x and y, right? The way we're doing the union is we need to find the root for x and y first, right? Because we then only only by finding the root node for those x for both x and y we know if the x and y they are in the same tree, right, or same components, right? And then we check if they're not in the same component. If they are, we can simply ignore it because there's no need to union it. And we just if they are not, we by comparing the rank, we will union those two components, right? And then after constructing those kind of the ranked the roots array, we have like a structure. We have a structure of this thing, right? So 4 pointing to 3, 2 pointing to 1, 1 pointing to 0. And then we just for each of the number here, right? For each number 0 to 4, we'll for each of the number we'll be calling the find to get uh their roots. And in the end, we just return the distinct root, that which will be our final result. Okay, cool, guys. I think that's it for this problem. I hope you guys like it. Yeah, and thank you so much for watching the video. I'm also learning about UnionFind. It's not a long code, but it's such a powerful algorithm. It can gives you a lot of benefits. I think there's also you can also I think check the if there's like a cycle in this graph, and by by constructing a graph, right? So I think let's try to explain this uh, imp another implementation, another use case for this union find, right? So let's say we have a 1, 2, 3, 4, right? And then let's say there's a 5, 6, and then it's coming back to 7, right? Let's say there's a graph here, right? So how do we use this union and find to detect a graph? So detect a circle, right? So first, since we have all those edges, right, we can create a graph. We can create a graph with like the root node with the node and all its like edges, right? Can conform through this two here. And so basically, we just loop through we while we're traversing this edge here, right? And for each of the this okay, not traversing edge. So we traverse from the this node here. Let's say we're traversing from the node here. So for 2 here, we loop through all its edges, right? And by the when we loop the edges, we will use, let's say for example this 2 and 3, right? And 4, 5, and 6. So for each of them, we'll be using the same, we'll be using the find method. We're using the find method to find that method's that nodes like the roots of that node. If the roots is the same same as this one, then we know there's a cycle, right? Because otherwise, yeah, because this, I think, sorry, yeah, because how can we detect like the cycle, right? Cycle, because let's say we're starting from this two here, right? Since we're doing like the DFS, right? For on each edge, let's keep like building this parent and child relations, right? So when it's coming to here, we build three and build with two. So now four, three, two, one, they are all pointing to one, and then five, right? And then six, right? Because each one has its own parent, each an edge, right? So by the time we reach six here, so all the six, five, four, three, two are pointing to one, right? And now we traverse back, right, to two. Now the second one, the other node, the other edge from two will be six, right? And then at this moment, let's say the two is also pointing to one, and then we see, oh, this six is also pointing to one, and then we know there's a there's a cycle here, right? Because let's say, for example, if we don't have this edge here, right? Going back here, two, three, four, five, six. So each time we check if the edge, if this edge like has the same parent node. I mean, before building before merging this node here, the parent of this node will be the node itself, right? This node's parent will be one, right? So that's how we detect the, the cycle. Cool. All right. I know it's a long video. Thanks for watching the video, guys. I hope you like it. So I know it's a tough one, but yeah, try to understand it. It's a very useful algorithm. Yeah. Let me know if you guys have any question. And then until next time, I'll see you guys. Thank you.